area units. So the main type of unit we decided last time was we measure things in squares usually. So if we take something like something that's 1 foot by 1 foot, then what's inside is 1 square foot. Which we can write a couple of different ways. We could abbreviate it square foot. Sometimes we'll write it as foot squared, literally foot to the second power. Now, what's going to happen sometimes is we need to pick an appropriate unit for a given problem. And so sometimes we need to switch from inches to feet, feet to miles, and so on. So sometimes we'll need to make similar transformations when we're looking at area units. So if we know something like 1 foot is equal to 12 inches, how do we convert that to an area measurement? And the key is in the picture. To go from feet to square feet, I have to multiply those measurements together, or in this case, actually square them. So consider squaring both sides here. What happens? Is it legal, by the way, to square both sides of an equation? You guys remember that from algebra way back? Yeah, it's legal. It's okay. So I get 1 foot times 1 foot, which is what we call 1 foot squared or 1 square foot. What happens on the other side? I get 12 times 12, which is 144 square inches. So although there's 12 inches in a foot, there's 144 square inches in a square foot. Okay? So we have to square any conversion factors we knew that were linear to get the metric equivalent. And that was one of the questions I think you were asking about there. So we have to make that adjustment if we want to make a transformation from one type of unit square feet to another type of square inches. So for example, if I have 1 square meter, what would that be in square centimeters? So write down what you know about meters and centimeters and see if you can convert it to an area measurement. Anybody remember how many centimeters in a meter? 100, yeah. So to do the conversion, we're going to have to square both sides of this conversion equation to get one that relates to area. So the left side is going to give me my 1 square meter, and 100 times 100 is going to give me a 1 with 4 zeros. So that means inside a square meter, there'd be 10,000 square centimeters. A whole lot of square centimeters. All right, so double check that I address that question. Yeah, so I'll just pick on one of these, or a couple of them. Can I blow this up? All right, sort of. Let's take so miles and acres is in the book, or you can look that up online. Let's take a look at 6,000 square feet compared to square yards.
That one I got, I just typed it in wrong.
Okay.
I separated it and then 120.
So what was the problem on that one?
I did it completely right.
Yeah.
I just, when I looked at my computer, at my calculator,
You just typed
it was
wrong?
104. When I typed it in, I typed it 120. I don't know why I did
Okay.
that.
All right. So you didn't have a question on this one?
No, that's the one I got partially right, but that one I understand.
So,
It was.
this is question number 4. Yeah, number 4.
Number 4 I thought. I just need to redo it, and haven't yet. It's
Okay.
10, 12, and 20. I was having issues with.
Yeah, we're going to get to those in just a minute. Okay. All right, so actually, let's get to that right now. I'm going to get this started with you, and then you're going to go get on a computer in a little bit and finish it. Oh, I better hold off on that then. Okay, we're going to skip that one for now and jump to circles. So this is where the video is going to get extremely boring because you guys are going to get up for a minute and measure some stuff. I have a bunch of round things up here. So I need everybody to measure 2 round things. And what you need to measure, I have some tapes up here, and you can partner up with somebody. You need to measure the circumference of the object in centimeters and the diameter of the object. And write those down. Give your object a little description, and then measurement of the circumference, measurement of the diameter. And we'll take a look at what we get with those. I'm going to make a spreadsheet to collect your data. So start measuring stuff. So if you're at home, find some circular objects. Circumference versus diameter.
Okay. You guys can measure this.
Got inches on one side and centimeters on the other side.
That's feet.
It's feet and inches. Yeah, so to measure with this one right here, it's to the tip. Nothing that way. All right, read a description.
Oh, yeah. Sorry. Thank you. I mean, it's wonderful.
All right, yeah. All right, I'm gonna measure stuff too.
So 10 4 tenths.
What do you got?
30 for the circumference and then diameter.
0.5?
Yeah, 9.5.
9.5. Oh, good. I missed the 9.5. And which object is that?
That would be this
All right, let's get that name. What's it say on there? Chips lid. Okay. Chips lid. All right, and did you get that yogurt lid too?
Yeah, this one was 54.5 centimeters. The circumference, the diameter.
Sorry, 50.
54.5.
54.5 and diameter?
17.
17. Okay. What do you got over there? You got a frisbee?
Yeah, frisbee circumference 74.5.
Oh.
Diameter
Big round one.
3.5.
Oh, okay.
Zoom in a little.
High
Pie tin.
is 36 plus you and 11.5.
36. 11.5. Okay. Anybody else have an object for me?
You have a fair trade can,
Okay.
32 inches circumference,
Centimeters?
10 years.
to circumference and
10 and 4/10 diameter.
1.4. Got it.
And
Okay.
then we have the coffee.
Good read on that. Wow, you are awesome. I was slaying and you were just right on.
Who's the teacher now?
Oh, you are ready to step down and let someone else take over. All right, what was the other one?
Circumference of the big coffee can
Yeah.
is 49 centimeters. Diameter is 15.
Okay. I think that's enough. All right. So what do these numbers have in common?
They can be used to find the area of a circle.
It could be used to find the area of the circle. Okay. How?
If you define the area of a circle with a circumference, it's C equals 2 pi r. So you take the diameter.
Whoa, whoa, slow down. Okay, that's a lot of information. Let me write this down, catch up to you there. All right, so some general information about circles from teacher Kristen.
That'll do. All right, so this is the circumference. Stuff. And then you mentioned a radius. That, oops. There can be the radius.
Which
Oh.
is half of the diameter.
Ah, so we also have a diameter, which we measured. Diameter. Something else I should point out here, the radius and the diameter intersect at the center. And then we have some area. Okay, so I'm not quite ready for area, but you made a statement that if you call the circumference C, it's equal to
2 pi r, which is also equal to 2 pi, like quotations, 1/2 times d. So if you only have the diameter, the radius is 1/2.
2 pi 1/2
Parentheses.
d.
You have to parentheses.
I have to put parentheses around the 1/2 d?
I guess so, so you don't want it to like interfere with the
What if I wanted to interfere with the rest of it? Oh! Let's see. What are parentheses mean when I put it in an equation or expression?
You have to do that.
It means do that first. So I can't go 2 times pi first. I got to do the 1/2 the diameter first. What does outside the parentheses mean? Multiply? Okay. Yeah, so just a reminder about the order of operations. The routine is usually multiply left to right, 2 times pi times 1/2 times the diameter. And we can put in parentheses to change the order, like Kristen said. Turns out multiplication has 2 lovely properties that allow us to basically do things in any order we want. And you remember those 2 properties? Associative and commutative property. Yeah, they allow us to do multiplication in any order we want. So it turns out because it's only multiplication, the parentheses are actually optional. We don't have to do it that way. We can mix it up in any order we want. And since pi looks like more like a variable than a number, I'm going to reorder this as 2 times 1/2 times pi times d. Anybody see an advantage to doing that?
It takes it into just 1, you eliminate the 2.
Yeah, 2 times 1/2 is just 1, and 1 times anything is just pi times the diameter. Okay, so now we've taken that down to C is the same as pi times the diameter, and we just took a bunch of round objects and measured on them the circumference and the diameter. What are we missing from our connection of 3 things a minute ago? Pi. Okay. So how do I connect the circumference and the diameter to pi? We have a couple of ways we can do it. You want to suggest one? What was that? Multiply pi by the diameter? Yes, that's a good idea, right? Because that's how we get circumference, isn't it? Yeah. So I'm just going to alter my table here. I'm going to call this measured. Move over. Measured circumference. Let's make it pretty.
And then we'll go make one over here called calculated circumference. Got pretty. All right, so I should just be able to take the diameter times what? Pi, what's pi about? 3.14 is what we often say. The computer has a version of pi in it. So the computer says it's more like 40.82. Is me saying it was 41 pretty close? Yeah, I don't think I can read 0.82 on that tape measure. Okay, so I did all right. And then I can just fill this down now that I've typed that in. Let's see how we did. 49.298, that's not bad. 32.65 versus 32. 36.11 versus 36. 73.79 versus 74.5. 53 versus 0.38 versus 54.5. 29.83 versus 30. Aren't we all pretty darn close on those? Yeah. Okay, so that's one way I could look at it. Is there another way I could look at these two numbers with respect to pi? What else could I do? Could I estimate pi based on our measurements? How would I do that? Yeah, instead of multiplying diameter over there, we could swing it over and say circumference divided by diameter is equal to pi. And this is how we discovered pi historically. People noticed that, hey, whoa, doesn't matter what circle I measure. Well, then when I take the circumference and divide by the diameter, I get the same other number that's around 3. And at first it was around 3, and then we got better and better at estimating or measuring it. So I'm going to now try to estimate pi based on our numbers. And so I should just be able to divide them. 41 divided by 13. 3.15. What else do we got? 3.15, 3.20, 3.17, 3.13, 3.07, 3.12. So we're a little high, a little low, kind of depends. Sometimes maybe we had a better diameter measurement than a circumference. Maybe we need better measuring tools. I wonder what happens if I average those? Will that even out our ups and downs? Ooh, not bad, 3.145. It's getting better. Had we measured more objects, we might, and been a little more careful in our measurements, we might even do a better job. What was harder to measure, the circumference or the diameter? Anybody have an opinion?
I thought the diameter was hard to measure.
I thought so too, because I was trying to get the edge and the center right, but the circumference I just wrapped around and looked where they touched. And that circumference seemed like a pretty easy thing to measure there. All right, so we have one super powerful thing that we can use to do things related to areas. We're working up to that area problem. All right, so I gave you guys a piece of paper with a circle on it. I would like you to cut that circle out. There are Kuipers up here. Help yourself.
Do you have any more?
I will print one right now. Where are we? I had it here somewhere. Dodecagon inscribed circle. There it is. So this is what we're doing for the audience out there in the future. I guess I need a copy of it too. Yeah, cut that circle out. I'll make 3 just in case somebody messes up their cut. All right.
Which line do you want us to come?
The circle, not the dodecagon.
I'm trying not to. Yeah.
Yeah, the outside is the circle, yeah. So this is a dodecagon inscribed in a circle. We want the circle.
Are you trying not to put up on others?
I don't think. Yeah. I got it already. It's all. Thank you.
And there's rulers out here. You might want one. If you have one of those cute little rulers I gave out earlier. Yes, no ruler.
Go on.
Okay. So then what you're going to do is once you cut out the circle, we're going to try and find its area. Each point on the dodecagon can be connected with the center. So draw those marks and then cut out those sectors of the circle. So what we should end up with, since this is a dodecagon, do is 2, dec is 10, 2 and 10 is 12. We'll get 12 relatively congruent sectors of a circle.
Are you talking about just 12 triangles?
Yep. Well, no, they're not triangles because the one edge is curved.
Oh, almost triangles.
Yeah. So when we cut out part of a circle through 2 radiuses, it's called a sector. So we will get 12 sectors. But it is interesting to note, like Kristen said, they are almost triangles. Pretty darn close. All right, dare I freehand it? All right. Once you get them cut up, you're going to attempt to assemble them into a parallelogram looking thing. I got a thumbnail of it up here on the screen. I'm going to rebuild my sectors into what looks like a parallelogram. Sticking together a parallelogram. This one up on the board. Whoa, that's big. Need to resize that. Do that again.
All right, so quick review from last class. We have some formulas. Rectangle, area, base times height. I like to call them base and height to remind us of the perpendicular qualities of those two numbers. They've got to be perpendicular. How about a parallelogram? What's the area formula for parallelogram?
Base times altitude.
Base times altitude, which is usually height is synonymous with altitude. Yeah, so I'm going to call that one base times height also. Again, they have to be perpendicular. Altitude also indicates that perpendicular nature. Yeah.
So on the homework, I was going over the book and then they helped me solve this.
Yeah.
It said you can take, so anything that has like regular triangles in it, so say a hexagon, you can take it and do the triangle formula and then times it by how many sides.
Yeah, we'll get to that.
Okay.
Yeah, that's that homework question you asked about. We'll get
Okay.
to that. Yeah, so the number of triangles inside centered, they have to be centered, is related to the circumference or the perimeter of the figure. Yeah, and a similar thing happens with a circle. Trapezoid, anybody remember that one?
Base 1 plus base 2 times the height divided by 2.
And I like to put the base divided by 2 and under the height base, 2 bases, but it doesn't really matter as long as you ultimately divide by 2. Because when I think about it, it helps me visually is if you average the 2 bases, that is basically turns it into a rectangle. And then triangle. One half base times height. Sure. A lot of people like to think of it as the base times the height divided by 2. And do you see any relationship between the trapezoid and the triangle formula? We didn't talk about this last week.
You just add a second base in there.
Yeah, so check this out. I'm just going to manipulate the trapezoid formula. So here's an example of a trapezoid. So this I could call base 1, this would be base 2, and then the height has to be an altitude, it has to be measured perpendicular. Okay, so that's my height there. So we said base 1 plus base 2 times the height divided by 2. So I'm just going to do a little algebra to this right here. I could say that both bases are divided by 2, so that's the same as base 1 over 2 and base 2 over 2. Okay, so that's that part, and that's being multiplied by the height, and they're both being multiplied by the height. So then what I have is base 1 times the height over 2 plus base 2 times the height over 2. And what are these things now that I've separated out here? They must be formulas of triangles, yeah. So we can just go up to the figure above and say, draw in one of the diagonals, like that one right there. And so we just found that area right there, and this one is that lower area right there, split into two triangles. So there's a couple of different ways to attack these geometrically to get a sense of why they work the way they do. Lots of wild relationships. All right, so with this one in mind right there for a parallelogram, let's take a look at that remixed circle we just made. So we took our circle and we reshaped it into this figure right here. And Kristen said those sectors are roughly triangles, and when I slap them together, I roughly have a parallelogram. So all I have to do is on this parallelogram, I just need to identify what is that altitude type height there. And then, let's see, what else do I need? I need the distance across here. That's what we call the base. Okay. So take a look at those sectors that you cut out. Given any one of these sectors, how is the height of this sector, this h here, related to the original circle? It is the radius, right? Yeah, this height here is the radius of the circle. Nice. Next question. I don't exactly have a parallelogram right here because this side really isn't straight. It's a bunch of little bumps. How are those little bumps right there related to the original circle? Yeah, that's the semicircle perimeter. Yeah, that's that distance right there. So my base, what I'm calling the base, is actually half of the circumference. All right, so let's see. So according to that, the area of my parallelogram should be just base times height, so that's circumference over 2 times the radius. Right, that's what we just built there. All right. What's circumference again, Kristen?
It's the measurement of
The formula, you gave me a formula earlier. Yeah.
Is C equals 2 pi r.
2 pi r. So we're just going to replace that. So right now we have C over 2 times r. C is really 2 times pi times r. So we just drop that in where the C was. So we just did this replacement right there. Oops, that whole thing. Can we clean that up a little bit?
Okay, you break the 2 pi r over 2 into 2 pi over 2, and then r over 2, and that goes with the r over 1. Okay, times those.
So you want to write that as r over 1 so we can multiply this stuff together? Okay, yes, we can definitely do that. So we're going to have an r times an r. We're going to have a pi. What else? What happens to the 2's?
They cancel.
Yeah, they cancel. We have a 2 divided by 2, which is 1. So we end up, based on the idea of cutting up a circle into pieces and what we know about a parallelogram, we now know that the area of the circle appears to be pi times the radius squared. Right. So just the cool thing about this is we can approach geometry experimentally. With the geoboard, we played around trying to find areas of shapes. We came up with formulas for parallelograms, for triangles, for trapezoids. We can play around measuring round things to try and figure out where pi comes from and how that relates to the circumference of a circle. And then we can cut up a circle and use all of that other stuff we know to try and find the area. So geometry doesn't have to be, these are the formulas because I say they are. You can kind of play around and explore and build into them. So where we spent maybe we spent an hour and a half playing with geoboards. With kids, you could spend weeks playing with the geoboards, getting those ideas out. It wouldn't happen instantly, because this is your second take on these things. All right, so we've got more formulas added to our list. All right, so one more topic, and then we're going to move on. Let's see, we still have to get to that question.
Kristen had. I'm not ready to do that one yet. All right, so, whoa. Interesting.
I mentioned the idea of a sector of a circle. So a sector of a circle is any time you take two radii and you use those radii to mark off part of the circle. So here, I'm claiming this part right here. Bless you. So that's my sector right there. And it turns out there's a cool relationship between the angle that those two radii make and the area of the sector. Okay. So what do you know about angles in a circle? We've talked about this before.
Like if you cut a circle in four, you can do 90 degrees. And
So each fourth of a circle has 90 degrees and a whole, because a whole circle has, yeah, if we go once around the circle, we have 360 degrees. So just a measurement, degrees are a kind of measurement. 360 degrees is equal to 1 revolution. Okay. In this picture up here, I've only made part of a revolution, right? Okay. So to find the area of the sector right here, all I have to do is make a note of what part I've done. Well, I've gone a total of whatever angle is, so I'm just going to call it angle still. Out of, what's the total amount you can do in a circle? 360. Yeah, so whatever that angle is out of 360, that's the fraction you've gone around the circle. All you have to do is multiply that fraction times the area of the circle. Pi times the radius squared. And that's how we end up with the area for a sector of a circle. Just a simple fraction. So for example, let's go for a very popular angle, not 90, but 60 degrees. And I want to know the area of this sector if the radius is equal to 3. So see if you can come up with a measurement for the area of that sector. It's a 60-degree angle, and the radius is 3.
we're trying to find the area of that
Of the sector.
sector.
Mm-hmm.
So have a formula. I don't know if this is right.
Well, we have a formula right here. That's what we just built off that picture. We're basing it off this formula right here. We just need to know what part of the circle we have. The angle measure tells us what part we have. Part of the whole gives us the fraction. I can keep cleaning this up a little bit. So without a calculator, I can get down to its 3/2 of pi. So it should be a little over 4.5 if you plug it into a calculator. Anyone get around that?
4.7.
4.7? Okay, that's reasonable. And be careful in the homework, sometimes they ask for an exact answer using pi, and so they're gonna want you to simplify it down. Sometimes they ask for an approximate answer also, sometimes they don't. It just kind of depends on the problem. So this would be the exact answer, and it approximates to, was it 4.7 to 1 decimal place? What's that?
3.7.
I think it should be bigger than that. Yeah, what'd you get? You go 4.7?
4.71.
4.71? 4 or 3?
4.
Okay, I thought you said 3.7. Okay, so to 2 decimal places, it would be about that, partway around.
Let's see here. I'm ready to do question number 20 from the homework. Take a look at this one. So question number 20 gives us a planet with a circumference of 39,750 kilometers. And we're asked to get the radius out of that, and then use the measurement in part A to determine the length of an arc from the North Pole to the equator. Screenshot that.
So here we want to make a connection between the circumference and the radius. So we have a couple of different circumference formulas. So given that we want the radius, we'll use the one that says 2 pi times the radius. And we're given 39,750 kilometers. I'll leave the kilometers off for now. Equals 2 times pi times the radius. So since the radius is connected to the 2 pi with multiplication, how do we break it? Division, yeah. So then that gives us that the radius should be whatever 39,750 divided by 2 pi is.
Let me ask the calculator. $39,750. So somebody could check on a calculator with me. Divided by 2 times pi. Google says it's 6,326.4-ish. So 63264. About. And in the next part, did they ask us to be more specific? Round to the nearest whole number. Okay, so they just want the 6326 part. And 4 means we leave that 6 alone. All right, measurement, use the measurement in part A to determine the length of an arc from the North Pole to the equator. All right, so to do that, I'm going to draw my best picture of a planet down here.
Planet's 3-dimensional, so here's the equator coming through and a dotted line going around. And then we've got a North Pole right there on top. And we want to get down to the equator. So we want that right there. Is that true? Okay, what can you tell me about that arc compared to a circle? Yeah, that's a quarter of a circle. So this is like if I threw perpendicular lines through there, that's going to give me 1/4 of the circle. So 1/4 of the circumference. We were given that the circumference is 39,750. So for that arc right there, we're just going to take 1/4 of it. So 39750 divided by 4, whatever that is. So I highly recommend drawing pictures when you do these. Picture will often lead to a solution. All right. So next, I'm going to do a demonstration in GeoGebra, and then in a little while, you guys are going to go to the computers and try and do it too, and I'll help you with that. But we've got a task to do in between. All right. So on the home page for the Chapter 14 stuff, I have a GeoGebra activity. And so I'm going to go through the steps that I list here. So I have some screenshots with what I'm about to do. And this is related to question number, I believe it's 10 that Kristen asked about. And we're going to eventually fill in this table. So I'm going to do one of them right now, and then you're going to go to a computer in a little bit and give it a try. So let's see, which app do I want? I'm torn as to which one's better, the geometry app or the classic app. I don't know if you guys have played enough yet to have an opinion yet. Anybody have an opinion yet? You've only used the geometry one? Okay. Yeah, because last time half the class ended up in one and half ended up in the other from different links.
I like the classic.
Yeah.
Because you explained it, because you were using it. The new app was harder, because you had to figure.
Yeah, I'm going to go for the classic.
Yeah, I like that, because I like how everything's.
Instead of down the side. All right, so the screen looks the way it does on mine, probably because I use GeoGebra a lot and it grabbed my default settings. I'm not positive about that. They seem to tweak things every time. So my goal here is to look at the idea of taking a regular polygon and splitting it into triangles where the triangles meet in the center. Now, since it's a regular polygon, then each of the triangles is going to have to be congruent, okay, because they're starting off with the same outside edge, and they're all going to the center of that polygon. So each of these interior lines is going to be the same. Now, these aren't, I can't quite call them diagonals because a diagonal connects two not connected vertices, and these don't do that. They just go to the center of the polygon. They're just edges of these internal triangles right there. And zoom in on this one. So here I've broken up my pentagon into triangles, but to do that I had to find the center first. To find the center, I had to draw a bunch of lines of symmetry, and it turns out lines of symmetry always meet in the middle. It's kind of nice, at least on a regular polygon. So the task in GeoGebra is to try to figure out how to use the tools to find the center, and then use the center to try and break down these triangles. So the key things I was looking for, I needed the center point right here, and I needed this midpoint on the other side. Okay. So this triangle right here, to find its area, I could use this as the base, which means I would need this height right there. And that height has a very special name. It's called an apothum. Not an opossum, an apothum. Okay. So we're going to try and find the apothum measure. In my table back here, we're going to want to know how many sides the thing has. We're making it so that bottom side length is 1. That makes our job way easier, okay, rather than some random length. So we have to find the height of the apothum, which is the height of the triangle. We need the perimeter. Is that going to be easy or hard to find? Easy for 2 reasons. Can somebody tell me one reason the perimeter is easy to find here? It's a regular polygon. All the sides are the same length. Okay, another reason? Yep, and our base is 1, right? Okay, so that part's super easy. The number of sides, that's also the perimeter here. Okay, so what we're going to look for is a relationship between the apothum, the perimeter, and the area.
is the goal of this right here. All right, so here I go to try and do that in GeoGebra. Where'd GeoGebra go? There you are. So first thing I'm going to do is I'm going to make a side of length 1. So let's see, somewhere in here, there's a tool that says, give me a segment of a specific length. So I'm going to use that tool. I'm going to just pick some point here, and I'm going to say I want length 1, and it's going to make another. I can zoom in on that. Super important when you're playing with GeoGebra, look at what tool you have before you do something. Otherwise, remember last time we had problems with we were clicking and weird stuff was happening everywhere. So I always have to stop, take a breath. I want the pointer tool to move things around. All right, so next thing I want to do is make a regular polygon. Anybody remember how to make a regular polygon? Yeah, the polygon tool, one of them says, hey, make a regular polygon. The order you click the points just determines whether it faces up or faces down. Doesn't matter. I can't remember ever which is which. So we'll see if I get lucky. If it faces up, what should I do? 4, 5, or 6? Any suggestions? 6. Ooh, not 46. 6. What do you think a 46 gon would look like? A circle. Yeah, it's going to look like a circle. All right, so there it is. Okay, so I got a move tool. Move it again. All right. So to find the I got to break it up into triangles, so I got to find the center in order to do that. Now, since this one's even, it's easier. If it's odd, it's an odd polygon, it's harder. So on this one right here, pretty easily, I can just draw some lines, like this one right here is a line of symmetry. I can easily grab another line of symmetry. If this was an odd polygon, I would have to bisect a side to make that happen. So I'm going to do it that other way just to see that line is going to meet these two. So I'm going to use the perpendicular line tool, I think, maybe. Try it. Ooh, down here, it's telling me what to do. Select a point in a perpendicular line. Let's see, can I just go, that going to work? Oh, it's going to want to go over there. No, I want you to be here. All right, that didn't work. How about points? The midpoint here somewhere? Midpoint, there we go. All right, now I can use that perpendicular line tool. So sometimes it's a matter of clicking tools in the right order. So all lines of symmetry on a regular polygon are going to meet in the same place. I just need to find that intersection point. So I like the organization of tools in the classic one. Geometry one's not bad. And then I just point to the objects I want to intersect, like this line and that one, and it finds me that point in the middle there. So other things I need to know here is the length of the apothem, and the apothem is that altitude there. So by angle measure here is also the distance measurement tool. And I don't have a line segment there, I just have a couple of points. So I'm just going to have to click from point to point, and it'll say, hey, the distance from here to there is 0.87. Okay, so make a note of that right now, that for a hexagon, that distance is 0.87. Grab this into my sheet. Screenshots. All right, so I got that one right there. All right, so next thing, what else am I looking for? I need the apothem. I've got the perimeter. I don't have the area yet, but remember, GeoGebra has a nice button to measure areas. So all I have to do is find GeoGebra and switch from measuring lines to measuring areas and click on the polygon. GeoGebra says the area is about 2.6-ish. Let's write that in. So the area is approximately 2.6 square whatevers. Okay. All right, so let's see, what's the perimeter here? Perimeter, because it's a hexagon, is 6. All right. And I asked you to, in the next column, multiply the apothem by the perimeter. So whip out your calculators. What happens when I take the apothem, times the perimeter? What is 0.87, that's a point there, times 6. Yeah.
5.22, twice the area, roughly.
0.22. So yeah, the area, 2.6. If we take the 5.22, cut it in half, we get about 2.6. So 1/2 the apothem times the perimeter. All right, so the area equals 1/2 the apothem times the perimeter. How do we get the perimeter? Yeah, we just counted the number of sides, right? Yeah, so in this case, the perimeter, because this is a hexagon, the perimeter is just the number of sides times the length of a side. So in this case, we have 6 times S. And so the point of this is just kind of 2 points. 1, play around with GeoGebra, get used to the tools, see if you can make stuff happen. And then 2, we're just kind of experimentally trying to find the relationship between the apothem, the perimeter, and the area. Okay? Apothem, the perimeter, and the area. So in a little bit, I'm going to have you guys whip out a computer and give that a try for the square and the pentagon. If you want to try again for the hexagon, that's cool too. All right. So
Are we like printing that out and filling it out the table?
you can just write it down on a piece of paper. Yeah. All right. So let's see. There was one more homework question to look at. Number 10, I believe. I'll have to zoom out to see this one. All right, so this one says, find the area of each of the following regular polygons. Type exact answers. So this is related to that whole apothem problem. Page. So let's do the hexagon first. So what length have they given us there? What's that? Yeah, they gave us the base here, and they gave us the apothem. So if we draw in that triangle right there, one of these triangles, the area is 1/2 times the base, 10, times the height, 5 square root of 3. How many triangles do we have? We have 6 of them. Yeah, so the area of the hexagon is going to equal 6 times all of that. All we have to do is clean that up. And that's essentially the formula we came up with. We've got the side length times the number of sides, and then we have 1/2 of the apothem times that. All right, what can be cleaned up here? Anything? 1/2 of 6? We're going to have 3 times 10 times 5 times the square root of 3. Without a calculator, we can't clean up the square root of 3. They wanted an exact answer, which means we shouldn't use a calculator. So 3 times 10 would be 30. Times 5 is 150. So then the computer wants 150 square root of 3. So that one right there. And the triangle one's a little easier, so I think I'll leave that for you guys to do. All right, so we're going to take just a couple of minutes break, and then we're going to play around with the Pythagorean theorem, and then you guys can play with GeoGebra.